wait a few minutes. So what we have seen last time was how to solve with this Phoenix script that I gave you. By the way, I put on the Hippocampus webpage 3 files. One is the geo file, the one to create the mesh. The other one is the, if I remember well, is the mesh. The last one is the Python script that I was obliged to change the name from Py into TXT because in fact Hippocampus webpage didn't like the PI extension. I don't know why. Probably there is some restriction. So in order to run it, probably you should switch back into Py into Py extension. But in fact, it's the file that we have seen together. I just changed the extension. So obviously, in that file, I will come back in a while on that. Probably not everything is definitely clear, but I hope that the structure is reasonably understandable. So the idea is that from that script you get the solution of the periodic of the problem on this periodic cell for the two unknowns, the velocity and the pressure. So remember that what we said last time. So that formulation is slightly different in terms of that weak formulation that we are using here to solve the problem is slightly different from the one that we have exploited in our analytical discussion, because in the analytical discussion we were using a test function having already being divergence-free test functions for velocity, which eliminated completely from the problem the P, the pressure. Obviously, if you are interested later, you can calculate, but it is not necessary to calculate the pressure to solve the weak formulation. In the weak formulation that we considered here, we didn't assume, because it's not so straightforward to do that, we do not assume test function space, test function elements being divergence free, and so we have to keep the pressure as one of the unknowns. So this is the solution of the problem that we got for the velocity field, for the x component of the velocity field, which obviously is periodic in x and y. This is quite evident. Similarly, we obtain due to what? Due to a gradient of pressure, a unit gradient of pressure oriented like that. So this is our alpha, okay, in this case. And for y, we get this kind of profile. Okay, so this is the dy. So the previous one, the dx, and this one, the dy. And then we have also the pressure. Not so nice. Something like that. is the profile of the pressure. Okay, so still periodic. In fact, we don't care too much of the profile of pressure, because, as you know, what we are interested in is the permeability K, and we know that Kxx and Kyx are what? Are the integral, are 1 by omega, the integral over omega f of Vx, no? Vx due to the first loading, the E1. And similarly this. Okay. Do you agree with this or not? This is what we have seen in the theoretical formulation, and so once you have this solution, you have just to apply this definition to calculate the two components of the permeability. I will show you in a while where is this calculation in the script. So essentially, you have the two maps of Vx and Vy, and you calculate these integrals, and then you switch into the solution associated to a unit vector oriented as E2, which describes now once again the gradient of pressure. So this was the alpha 1, let's say, and this is the alpha 2 equal to E2. Okay, so the profile that we will obtain is exactly similar to the previous one, just turned of 90 degrees. I have to rerun the code to show you inverting just the loading, and from there, from the solution that you get from Vx2 and Vy2, you will get the Kxy will be 1 by omega, the integral over omega f of Vx2 dv, and Kyy 1 by omega, the integral over omega f of Vy2 dv. Okay, and so with these definitions, so essentially the Kx and Ky first index, second index, x will be the average of the velocity field induced by an horizontal unit gradient of pressure, and these ones with the last index y will be the average of the velocity field due to a unit gradient of pressure along the E2 direction. So according to the symmetry of the problem, the result in this case is just that obviously you should expect, independently of the symmetry, that these two, independently of the symmetry of the geometry, you should expect that these two are equal, because we have proven that the permeability tensor is symmetric. So independently, you can construct the geometry as complex as you want, the result must be that these two are equal. In particular, because of the symmetry of the problem, what we get here is that these two are 0. Almost 0, I mean 10 to the minus 6, 10 to the minus 9. With respect to a unit, or consider that here everything is many dimensions, so I was working with a unit square. So to simplify as much as possible. Also, the viscosity has been taken equal to 1. Okay, in any case, is, these are 0, and these kxx and ky are different from 0 and also different one from the other. No, sorry, in this case they are equal. In this case they are equal. In this case they are equal because the two profiles are exactly the same. So in this case, this is equal to ky. So in the end, the result is that the permeability tensor, the permeability matrix, is just a scalar k times the identity. Okay. Okay. So in this particular circumstances. Oh, just so just to let you so you see among the different part, at the very end of the script, there is this last statement which calculates the average of the solution. So essentially we are calling one of the functions that were previously defined. When you see this FEM assembly scalar, or assembly vector, in this case scalar, because we are working with the components of the solution, component by component, you are, when you see this FEM assembly, this corresponds to doing the integral, essentially. And the 1 by omega is 1, so it's a unit cell, so it's 1 by 1 square, so it's just 1. So these two lines give you the average velocity. So the output that you get from this script is giving you the average velocity for x and y. So for instance, if we run this. So you see that the result, okay, previously he calculated a couple of norms, don't care about this. Here you see the average velocity ux and average velocity uy, which are these two. So this is the average velocity along the x direction, and you see that along the y direction, with respect to this, it's almost 0. Okay, so we consider that this is a numerical sum. So this is 0.02 mainly, the kxx and the kyx is 0. If you, this is these are the results of the case associated to a force. This is the force vector, which is 1, 0. You see that in the weak form we have the bilinear form, which has been stated here that we discussed last time, and the linear form, which is the f times the velocity. So you have just to switch this vector into 0, 0.0 and 0, and 1.0 in order to get the other solution, and consequently with the averages calculate the kxy and the kyy. Okay. Okay, so this is what you have. What I asked you, I sent you a message a few days ago. What I asked you, and we discussed also quickly this last time, is to modify this formulation in order to introduce at the level of the mesh. Let me see if I have the mesh to show you. This, for instance, so the idea is that you have modified the geofile introducing this additional circle, so as an additional curve, and construct now the geometry as the difference between this curve and this curve. Essentially, when we specify the surface, we specify the surface just giving this line. You have to add also that one. In this way, you will generate later the domain like that. So the difference between the domain included into the first curve minus the one included in the second one. So this part of the region, and then you create the mesh. Okay, so this I think you can do. You have just to parameterize as I told you, you have just to parameterize the problem in terms of the coordinate of the center and the radius of the circle. So the idea is to, once you have found the way to construct correctly the geometry, you have to construct the mesh, keeping in fact the idea is to generate more than one file. Obviously, once you have generated one, the other ones are trivial. In order to let the circle change its position within a certain interval that I suggested you, and also considering different values of the radius, in order to understand how later the permeability will vary. So the idea is to take the original file, introduce this additional surface, this additional curve, to generate this new surface with a given center and a given radius that you can later change and mesh the domain. Once you have done that, obviously you will come up with a new MSH file. Okay. And this new MSH file will be read by your script that you have also to modify, because if you remember here, we were reading this file here, which was exactly the mesh file generated by GNSH. Now it will be different, so you could call it differently. And then what is the main point? The main point is that you have to slightly change what? Essentially, you have to take into account that you have another boundary. Huh? You have another boundary, and what kind of condition you should assign on this boundary? According to your understanding, we have our problem is still the Stokes problem, no? So for the Stokes problem, I remember you that on the external part of the boundary we assign periodic boundary conditions. No? For instance, the velocity there is the same as here, the velocity there the same as there, and here what did we assign?
Velocity equals to 0.
Hmm? Velocity equals
Zero.
0, okay. Which was the standard condition that we have when there is a flow on a wall. Huh? So here on the boundary of this circle, what is the condition that we have to assume? Velocity equals 0. Huh? Velocity equals 0. So essentially, what we have to do, what you have to do, is to modify that part of the code where yes. So you can do this in two ways. Either because the point is, if you remember, we characterize the region where to assign zero velocity directly giving it a label in the GMSH file, which was the label 5. So here we were just identifying the interface degree of freedoms, locating topologically them. I remember you that these were two different ways to locate the points, but finally we can use this. So we with this instruction we were calling interface degree of freedom those ones belonging to the part of the boundary labeled as 5. Okay, and then on this degree of freedom we assign the no-slip value, so 0 velocity, with in the space B. So what you can do is just to modify, probably the simplest thing is to modify the definition of 5. Because 5 in the GMSH file so 5 was the physical curve 5 was just the curve constituted by 6, 4, 2, and 8. 6, 4, 2, and 8 were these parts. If you remember, you can scroll this, were the circles. 2, 4, 6, and 8. Okay, so the physical curve 5 is this. So you have to add to the physical curve 5 this other circle. So you have to define here this other circle properly and to add this circle to the physical curve 5. So at this level you have to modify this definition of the physical curve 5, and as I was telling you, you have to to modify at this level the plane surface one, which is no more 9. 9 in fact, this plane surface 1, 9 means take the plane surface as the one generated by the closed curve 9. So you have to consider the two curves. So if I remember well, it's just a matter of adding here the other curve, but you can check them. It's quite simple if you look at the documentation of GMSH, how to generate an extruded region. I think if I remember well, you have just to put here the second closed curve, so the circle in this case. Okay, so if you, so essentially the idea is that if you modify here the definition of the plane surface and there the definition of the physical curve 5, then everything should be ready because
Professor? In the geo file, you have to change in the circle 2, 4, 6, 8. In the geo file, you show it before. So this we do not have to change in the circle because in there it's already the velocity is 0.
Here this is purely geometrical.
Yes.
Okay, so here this is just the definition of the domain. The only so you have to add obviously the additional curve. You have to specify that the region is extruded of this circle. The only relation with boundary conditions stay in the fact that we assigned later in the PI file the zero velocity on this physical curve 5. So if you add to this physical curve 5 also the internal circle, it's fine. Okay.
So one thing I want to ask, you gave us the text file, so we have to run it in the Python.
Yes, we have to change it into Py. Probably, I don't know if probably it will run also like that, but I suggest you to come back to the extension Py. If you run it like that in Phoenix, it will produce the result that we have seen together. Okay? But then you have to modify the script in this way to incorporate the circular inclusion. So first of all, you have to modify the geo file in this way. You generate so the new domain. Once you have, and this you have to check if everything works correctly, you should be able to see something like that before. In fact, at the beginning you should see this without the mesh. Then you go into the GMSH software and you generate, you enter in mesh and you click on 2D and you generate the 2D mesh, which should be something like this. Okay? So this you can obviously see if everything has been correctly done. You should be able to mesh only the domain which is interesting for you. So this part should be excluded from the mesh, obviously, because this is not part of your domain, the internal of the circuit. Okay? So if everything has been done correctly, this should be your results. And then when you go, so this you have generated the mesh, and then if you go into save, it's quite trivial. In this list of options of the mesh item, you save the MSH file. So the new MSH file, which is the new mesh file, that you have to give to your Python script. And so with this new with this new MSH file, normally, if you have just included into the domain, which is into the subdomain labeled as 5, this circle, normally you don't need to change anymore the Python script, because in fact in the Python script you just look for the domain labeled as 5 and attributes it vanishing Dirichlet boundary condition for the velocity. Everything else remains the same. Okay. So at this moment you run the two cases with alpha 1 equal 1 0 and then alpha 2 equal 0 1, and you will get you calculate the averages and you will get these first two couples and these second two couples of average of components. So this let's say that this will be, so KXX will be the dx average, KYX the Vy average 1, and similarly for these two. Okay. And so the point is that changing the position of the circle and modifying its radius, you will observe a certain number of conditions in which, first of all, you can obtain, rather than a spherical tensor, so just a permeability, you can get situation like this, with KXX and KYY different one from the other, but still diagonal matrix, or even the case, the completely anisotropic case, obviously still symmetric, these two should be equal, but different from 0. Okay. This is related, the fact that you can have these two terms or not, essentially is related to the fact that if you consider this geometry, it depends where you place this the center of this circle. If you have some loss of symmetry in the positioning of this circle when rotating of 90 degrees the figure, no? Because essentially you are considering the same problem with A1 unit force or an E2 unit force. So if the two configurations are equivalent when turning of 90 degrees, you could get a different kx from a kyy, but you will get the same kxy equal to 0. On the other hand, if there is some difference between these two configurations, for instance, the position along x and y is not the same, so this is out of the diagonal, then you will get also some kxy different from 0. So this you can check. You can exhibit few results of changing these parameters, the center of the circle and the radius of the circle, according to what I asked So try to do this. I think it's a nice exercise. I consider that this is part of the final evaluation. I would see how much you are able to do, but essentially you don't need to change a lot of things. So I think that you should be able to manage. Okay.
Professor, what, can you go over which programs you need to download
Sorry?
to run it? What are the programs you need to download, like this one here, and can you give us
The
a-
Phoenix, this is the, I told you, no? This is the Python script is written in Phoenix X, what you are using with Loran. So it's
Yeah, but-
exactly the same software that you are using. The additional software that I'm using here in parallel is the GMSH software, which is the one which is still open source, which is the one that is used to generate mesh. Nothing more than
Yeah. The problem with Phoenix only runs on Linux and Mac.
no, it should be of course.
It doesn't work on Windows. We tried it before and we have to download Linux.
This seems quite strange to me. I mean, I'm using Linux, but I don't think that it doesn't work. So with Loran, how are you doing?
We tried to use it but encountered difficulties, so we didn't use Phoenix, we just used NumPy.
Use?
NumPy, we just did
Ah.
it manually.
Yeah, but NumPy,
I don't know if it's possible to do.
but it's not sufficient because you need a certain number of functions that are of Dolphin. Dolphin is the
Maybe that's the one.
Dolphin should be next.
Dolphin is within
NumPy is
Phoenix.
alternative.
NumPy is just Python essentially.
Yeah.
So NumPy contains a certain number of basic functions that you can use to program in Python. Instead of reprogramming everything by yourself, you can use that. But it sounds a little bit strange to me that I'm not sure that, but I think that Loran is running on
Isn't it?
Linux. I put it on Windows. Yes, and Mac. Strange. So normally there is a way to install Phoenix X via on Windows. No? Did you follow the?
Yeah, you can install it, but it doesn't, there's some sort of stability error, and it always, it can run the first few lines of something, but we looked at it.
No, I think that the
It
problem,
just
because this is a
crashes.
similar problem that I experienced. So you get errors. It's not a matter that you are not able to run.
It
Yeah,
runs like, he gave us a code to run, and it ran like the first 10%, and then it crashed.
But it crashes. It
Or
gives
it-
errors.
It gives errors.
Errors. So I think that the main point is this, that you probably didn't install the Phoenix X version, because the problem of Phoenix is that they switched from Phoenix into Phoenix X. Phoenix X is the new version. And so from one version to the other, what happened is that they change a lot. And so the way in which plenty of functions are defined is different. and so it doesn't recognize the syntax that is used in Phoenix X because indeed you are not running a Phoenix X software, but a Phoenix software, which is the ancient version. So probably you didn't download the last version. You have to check this if you have downloaded the Phoenix or the Phoenix X, because once you, so it's not a matter of the fact that you are not able to install the software. It's a matter of the fact that you install the ancient version. I think so. No, because I tell you this because me too at the beginning, as I had the ancient version of the code on the laptop and I was not using since a long time, I just thought that I could basically update the file or having the two installations in parallel, which doesn't work at all. So you have to remove the Phoenix version and install the Phoenix X. So try this because I think that this is the problem. It's not a matter of Windows. It's a matter of the fact that the version that is installed is not the last one, and I don't know on. Yes, I think that you should go to the Phoenix X web page and download from there the good file to install. But pay attention to go here and not there, because that one is the ancient one. So you have to look for the Phoenix X version. Try with that one, because I think that this is the problem. It's not a matter of Linux or Mac or Windows. Okay, so, but in any case, this is just a tool to show you how we can solve problems as the ones that we have formulated, and in general, it's not, for them, finding an analytic solution, it's not possible at all. When the geometry is quite complicated, you cannot expect to find an analytical solution. So even without this hole, the solution that we found is obviously different from the estimate. This you can, even without this modification, you can check that the permeability K that we have found, Kxx equal to Kyy, is different from the estimate that we got considering just the channel like that, no? The estimate from below and from above that we constructed clearly, because the solution is more complex than that, than just a channel. That one is a good idea for having an estimate of the solution, but no more than that. Okay. Okay, so try to go to this installation. I don't know how does it work in Windows, but in Phoenix, what I went through is an installation via Minibomba, and then generating this Phoenix X environment. And so within this Phoenix X environment, I installed the Phoenix code. Okay. So now let's come back to our. We have to go towards the end because we have the last. These are the last three classes. So essentially, we have used the permeability problem, the Stokes problem, sorry, to describe the homogenization process. But if you remember, when I started discussing this this problem of homogenization, I told you, okay, so let's start from the hypothesis that the velocity and the pressure are purely periodic functions. And so we went through all these analyses, which took a certain number of classes, but keeping the hypothesis that the velocity and also the pressure is periodic. I told you this is not the best idea to assume a pure periodicity of these fields, because as we are also considering periodic microstructure, so our domain is constructed just as the union of several cells having all the same shape. If, and as we are just working on one of these cells in order to calculate our permeability, for instance, clearly what we obtain from here is a certain permeability and a certain average velocity. From there, we will obtain the same permeability and the same average velocity, because the fact that the average velocity just depend on is just periodic. So we said that V of Z is periodic with respect to Z. So as it is periodic, the average value within this cell will be the same as the average value within that cell, and so on. Okay. So this means that the global solution, the expected global solution, will be a constant velocity, which is not so nice in the end. So we need to understand how to extend this formulation to a more general one, which will be the one that we are finally going to use. But you will see that all the discussion that we have had, and in particular these solutions of the cell problem, will remain valid with a suitable rescaling of the problem. So the question is that we have to finalize our discussion and so move to the step 3 that we introduced at the beginning, so a formulation of the homogenization process based on double scale homogenization. Essentially, this is also what we have seen, that you have seen during plenty of presentation during the school, the summer school, the autumn school. So the idea is this: imagine that you have your periodic microstructure. This could be something like that. Let's start from something like this, and then we will generalize to a quasi-periodic microstructure, in the sense that the cells are of the same size, but eventually the inclusion could be affected by homothetic, so it can change of volume, just the inclusion, not the external cell. So the idea is, from the geometrical point of view, let's first of all introduce two coordinates, a kind of macro scale coordinate and a kind of micro scale coordinate. So each position x within this domain is split into the coordinate of the centroid of the singular cell plus epsilon y. So epsilon in this case is the characteristic size of the units of the cell. The idea is that at the beginning, let's say this, at the beginning we have a characteristic size L, which is the characteristic size of the domain, and a characteristic size small l, which is the characteristic size of the cell. So instead of working with finite dimensions, we rescale everything, and so we consider that epsilon is defined as L, small l by capital L. Okay, so the idea here is that you you have a unit domain of the, or a domain of order 1, of characteristic size of order 1, and a cell having a characteristic dimension of order epsilon, okay, because it is this ratio. And each one of these cells is the copy of a unit cell. So this is a unit cell, a prototype unit cell, which is rescaled by epsilon into that. Okay, so essentially you have your domain, which is a unit domain. Your cells, which constitute the unit domain, which are of order epsilon, which is L, small l by L, by capital L. But each one of the cells is constructed starting from a prototype cell of order 1, where we define a y coordinate ranging between y is a vector, so it's y1, y2. Ranging between minus 1/2 and 1/2. This is not correct. We did 10 times minus 1/2, 1/2. It's a vector, yeah? Okay. So, so the idea is, in order to characterize the generic coordinate of a point within the whole domain, we consider the xij plus epsilon y, where xij is just a kind of discrete variable because it's just the position of every centroid. So if the cell is of size epsilon, you have to count how many cells you have along x. So 1, 2, 3, and 4, for instance. Along x, and 1, 2, 3, 4, 5, and 6 along y. So this will be 4, 6 times epsilon in this particular case, plus epsilon y, which tells you where you are within the cell. Okay. So the idea is just but this is purely geometrical decomposition of a vector into the sum of two vectors, but the idea is that one is referred to the position of the centroid of the cell, and the other one is based on the y coordinate defined in this unit prototype cell. The discussion that we are going to deal with is restricted to the, let's say, to the central part, to the central core of the domain. So I'm not going to investigate what happens close to the boundary, okay? Because it's more complicated stuff. Probably you are going to see something about that with Patrice Cartreau, I don't know, on other kind of problems, but partly he has shown you this during the class of the school. It was probably too fast, but I don't know if he's going to come back on that subject or not. In any case, what we are going to do is to assume that the points that we consider are sufficiently far from the boundary in order to avoid to play with boundary condition assigned on the external part of the domain. So we will directly then assume later boundary condition at the microscopic level. Okay. So we have to come back to what we said at the beginning of our discussion. So the fact that we assume separation of scales. Separation of scales, if you remember, was introduced in order to take into account the microstructure, but in a situation where microscale fluctuations are not directly affecting the macroscale properties, just affecting macroscale behavior via suitable average quantities, as for instance the permeability that we are looking for. Okay. So the main idea was that we have a clear separation of scales between the microscale and the macroscale characteristic lengths, no? And this hypothesis reduces in our case to the condition that this ratio epsilon, which is the ratio between the characteristic length of the cell and the characteristic length of the domain, is much smaller than 1. So the idea is that the analysis that we are going to introduce is valid in the limit when epsilon tends to 0. Okay, epsilon much smaller than 1. And in these circumstances, the result that we are going to obtain can be extended even to more complicated microstructure, but having keeping this property, we don't need in fact to describe in all the details the microstructure, the real microstructure, but we can refer to this kind of prototype solution. This we already said, so I will not come back on this. So the main assumption that this separation of scale implies is the following: that obviously what we are going to do is to play with a differential problem, no? For instance, the Stokes problem, but we will see later also the problem giving rise to the bioconstitutive relation that we already met in porous media. So every field that we are going to play with is not just a function of x, of z, beta, the variable that we used before, but can be considered as a function of two separated variables, a macroscale variable and a microscale variable. So essentially every field, and in particular the velocity, but also the pressure, and the displacement, for instance in the case of solid, will be considered now as a function of x and y. Okay, so instead of having a field v function of z, periodic with respect to z, we will consider function v of x and y, where x is the macro scale variable and y is the micro scale variable. Essentially we are using, in principle we should use xij and y, okay? But as we have this relation between xij and y, by using x or xij is the same, and so we prefer to use a continuous variable which is x. Okay, so we interpret x as the macroscopic variable and y as the microscale variable, knowing that y is nothing else than x minus xij by epsilon. Okay? According to what we wrote there. And in fact, this xij is even not so important, because in the end it's just a constant, and as you will see, the main idea is that as we are considering every field dependent on x and y, when doing the derivatives of this with respect to x, we should consider this definition of y in terms of x and epsilon, and so in the end what is significant is just the dependence on x. This xij will be taken as a constant. So this I will show you in a while. So let's say this. So the main idea is that we switch from a completely periodic function depending on z, where z is the generic coordinate in the domain, into a function v depending on the microscopic variable x and the microscopic variable y, where y is the microscale variable and the function is v is y periodic. So the main point, the main difference with respect to the previous formulation is that now we have no more full periodicity, but we have periodicity only with respect to the variable that describe oscillations within the cell. When you switch from one cell to another, you have still this x which can change. Okay.
Professor,
Yes.
so if x is defined in terms of the discrete and the continuous or the periodic y, why are we writing the velocity field as a function of both? If the x contains both.
Why we are varying the field v as a function of
You write here v is a function of x and y,
and y, yes.
but y is also included in x.
Yeah, this because the idea is exactly this, is the fact that as we are introducing this scale separation, what we are saying is that essentially the velocity is the superposition, the pressure too, is the and to characterize the variability of the velocity, there are two effects. One of the variability of the velocity on the macroscopic scale, so the large scale variation of the velocity, and the other one are oscillations within the cell. Okay, and we can superpose these two variations, considering the two variables, because in fact one is not affecting directly the other, because of scale separation. This is an hypothesis, and it's a starting point. So we are the key assumption is this: that according to the fact that we separate scales, we do not expect to have this kind of behavior. So the fact that oscillations at the microscopic scale directly induce oscillation at the macroscopic scale. Oscillation at the microscopic scale will only affect average quantity that we will later use in the macro scale analysis. Okay. So this is a way to incorporate the local variability, but then keeping maintaining the possibility of having a variable velocity field, slightly variable velocity field, just because of purely macroscopic loading. Okay, so this is a starting point. I mean, what I'm saying is that according to this assumption, I'm not expecting this kind of behavior, and so I assume It's not a deduction, it's an assumption. I assume that my velocity field can be decomposed in this way. Okay, it's justified assumption, but it's an assumption. So you can convince yourself that it's a good assumption, but you cannot prove that it's a good assumption because it's an assumption. Okay, so this is the starting point. So in the end, every field that I here calling phi, but now we will specialize to velocity, pressure, and later to displacement. So every field, which was a function parameterized by epsilon, just to underline the fact that there is this scale separation, so the epsilon parameter is part of the game, which was a function of x, now is considered as a function of x and y, where the y is the ratio x by epsilon, x minus xij by epsilon, but as you will see, in the end, I can forget this xij, okay? So, this is an important point. Why? Because obviously, when playing with this field, phi epsilon of x, then we have to consider derivatives of this object. Derivatives with respect to what? With respect to time, okay, but more important with respect to x. So when introducing derivatives with respect to x of this, clearly this would imply to derive this phi hat with respect to the first variable, okay, but also with respect to y, and to derive y with respect to x. And so a term 1 by epsilon will come out. When you, this way I will show you the detail, but mainly when you calculate the gradient of phi epsilon x, this would be what? This would be the gradient x of phi hat. So this is important to distinguish between this and that. So this is a kind of partial derivative, partial gradient, because this phi hat is a function of x and y. Say, so gradient x of phi hat plus what? The gradient y of phi hat times the derivative of x by epsilon with respect to x, so 1 by epsilon. So the gradient of your function, of your unknown phi, will be translated into a gradient x of phi plus a 1 by epsilon gradient y of phi. Why this is important? It is important because we know that the analysis that we are carrying out is for epsilon much smaller than 1. So for epsilon tending to 0. So these two terms are not of the same order with respect to epsilon. Because when epsilon is quite small, this is much larger than that. This is of order 1 with respect to epsilon. This is of order 1 by epsilon, so this is larger. Okay, so the point is that you have to keep in mind that this decomposition of the gradient, and obviously when you have divergence, gradient of divergences, so you have to play with this nested sequence of derivatives. But what we are going to do is to play with the order of magnitude of the different terms, considering this 1 by epsilon coming out from our derivatives. Okay. So what is? So this is the starting point. This with a field V which is y periodic. So it's a function of x and y. Remains the macroscopic variable. Y will be the microscale variable, and the function is periodic with respect to y. So, as I was telling you before, in principle, this schema will allow us also to describe a situation like that. You see that the cells, the external size of the cell is the same, but the inclusion changes from one cell to the other. So this is what is called the quasi-periodic cell, quasi-periodic system. So formally each cell is the copy of this unit cell, but with a different size of the whole. Okay, so so what is the scheme that we have to follow? The scheme that we have to follow is this. So we start from this scale separation, and the analysis that we are going to do is based on the different terms coming out from the set of partial differential equations describing the problem, considering the different order of magnitude with respect to epsilon of the coefficient involved in the equation. So let's try to describe term by term, item by item, this procedure, and then we will start applying it to the Darcy law. So the first point is this: write the dimensionless formulation of the problem. So if you remember the Stokes problem that we have written was this mu Laplacian of V minus gradient of P equals 0, no? And then divergence of V equals 0. This is not dimensionless. The physical dimension of every term here is a pressure, so Newton by square meters and 1 by length, no? Because it's a gradient here. So the physical dimension of this is the one of a force per unit volume. Okay. And the same here, obviously, first of all, because the two terms should be homogeneous, but also because mu is a viscosity, so is Newton by square meters times second, the viscosity. The Laplacian is 1 by square meters, because it's a second derivative, and then you have the velocity, which is meter per second, and so in the end you have the same, obviously, the same physical dimension. Okay. This is, on the other hand, a 1 by meter, which is the divergence. It's just a derivative, and then meter per second. So this is 1 by second. Okay. So neither this nor that are dimensionless. So what you can do is you can just reduce this to a dimensionless form, saying that you introduce a characteristic length. Imagine that you say that the velocity v is a L by tau v theta. So what I'm introducing is a dimensionless velocity, which is an unknown clearly. So I'm just changing the unknown v into p tilde, which is dimensionless because it is multiplied by L by tau. L is a characteristic length, for instance, the characteristic length of our domain, and tau is a characteristic time. And we will see how to define it. But for the moment, it's just a characteristic time of the process. Okay? So this is V. Pressure, similar. So, sorry, this is then the derivative, so the length, obviously, x and y, so x in the sense of the vector, is L x tilde. Okay, y, so x1, x2, no? xi, let's write it like that. Just to indicate the three components, the two components. So this is dimensionless position. What about pressure? The same. P is P bar P tilde. P bar is a characteristic pressure. And P tilde is our new unknown. So the new unknowns are P tilde and P tilde, dimensionless unknown. Unknowns. And the dimensionless independent variable is x tilde. This, has nothing to do with homogenization. You should be reasonably familiar with the dimensionless formulation, because also from the numerical point of view, it's much better normally working with dimensionless equations than dimensional one. Why? Because if you have a coupled problem, typically it could happen that the physics of the problem, of the two equations describing the coupled process, is quite different. So the order of magnitude of the different terms involved in the coupled equation is strongly different. So if you use the dimensional version of the problem, you will write a coupled problem with matrices having values of the coefficient very different one from the other, which is never a good condition when you play with numerical resolution of differential problem, but even algebraic problem, in particular algebraic problems, because you have ill-conditioned matrices. So you should try to reduce as much as possible these oscillations, and one way to do that is to play with dimensionless variables. So this is what we can do. So we switch from P and V into P tilde and V tilde, and so this equation now, how does it read? For instance, it reads like that. You have at the place of mu Laplacian of V, what do we have? We have mu. The Laplacian will produce a 1 by L squared, no? Because it's a second derivative. Then you will have the Laplacian tilde. So what I'm saying is that the three coordinates x are rescaled by L. And so every derivative, when I have d by dx I, this will be 1 by L d by dx I tilde. Okay. Do you agree with me or not? So this will be mu 1 by L squared, the Laplacian of V, but V is L by tau V tilde. Okay? Minus the gradient of pressure. And the gradient of pressure is 1 by L, which is the gradient tilde of the pressure, which is P bar P tilde. Okay? Equals 0. So now if you rearrange things, so you can simplify this with that. So you have mu by L tau, Laplacian of Laplacian tilde of P tilde minus P bar by L gradient tilde of P tilde equals 0. This is still dimensional, this equation, because it involves dimensionless equation, dimensionless parameter, but the physical dimension of the equation is still that of a pressure by a length. Now, if you divide everything by P by L, P bar by L, this can be rewritten like that. L by P bar, L by P bar, mu by L tau, Laplacian tilde of P tilde minus gradient tilde of P tilde equals 0. And this guy is dimensionless, because if you remember what we said before, mu is Newton by square meters Newton by square meters times second. P is P is Newton by square meters, so you have Newton by square meter per second by second times second, and Newton by square meters times second. So at the denominator and at the denominator, and so this ratio is dimensionless. Okay, so this is a dimensionless number. So what we got is that our Stokes problem, our the first equation of the Stokes problem, depends on this dimensionless number. Okay, because here you have 1. Okay. The other equation is trivial, because the other equation was divergence of V equals 0. The other equation was this, divergence of V equals 0, and obviously it translates into 1 by L by tau divergence tilde of V tilde equals 0. But as this is equal 0, this you don't care at all, no? You just, in order this to be 0, divergence tilde of V tilde should be 0. So in the end, your problem reduces into that mu tilde Laplacian tilde of V tilde minus gradient tilde of P tilde equals 0, and divergence tilde of V tilde equals 0, where I called mu tilde the dimensionless ratio mu by P bar tau. Okay. So what I have got is that now the problem has been written in a dimensionless form, and identified a dimensionless number, which is the only number that characterizes my problem. Okay. So what is the idea? The idea is, so first of all, write the dimensionless formulation of the problem. We have written this for the Stokes problem. We will see how to write similarly when playing with displacements and stresses and so on. Identify the dimensionless numbers, in this case just one, the mu tilde, and this is the fundamental point, characterize them with respect to epsilon. So the idea is that at this moment we have a set of dimensionless numbers, in this particular case just one, but we can have more, and we state assumptions on them with respect to their order of magnitude relative to epsilon. Epsilon is a small dimensionless parameter, is the small l by capital L. Okay. So what we are going to do is to state what is the order of magnitude of this mu tilde in particular with respect to epsilon. Clearly, depending on this assumption, this assumption, let's say this assumption will affect the final result. So depending on the hypothesis that we are going to do at this level, on the order of magnitude of these dimensionless numbers, the final problem that we are going to obtain via homogenization could be different. But what does it mean, assuming an hypothesis on that? It means, for instance, here, if we say, typically what we say is that this mu tilde is of order of epsilon square. This is what typically we assume. So this means that the ratio between mu and p bar by tau is of order epsilon square. Okay, so this means that for epsilon tending to 0, this ratio is tending to 0 as epsilon square. So this is going to 0 much faster than p bar tau. Okay. So it's an hypothesis of our model. It depends clearly on the process that we want to describe. But this is a fundamental point. So we have to fix assumption on all the dimensionless parameters appearing in our formulation. Why? Because once we state this, for instance, we will rewrite this mu tilde as epsilon square mu bar, let's say. Okay, so mu bar now is an object of order 1, and so a constant. We don't care about it. Okay, we care in the sense that it's a number, but it's no more affecting significantly the problem. But we make explicit the order of magnitude of this object via this epsilon square in front of mu bar. This is important because now this term here is going to interact with the epsilon coming from the derivatives. Because for the moment I didn't use this decomposition. I've just rewritten my equation in a dimensionless form. Then, as we will see, we use the hypothesis of scale separation, and we let enter in the game epsilon also via these gradients. And this will generate a cascade of problems. So let's go step by step. So for the moment, write the dimensionless formulation of the problem. Okay, done. Identify the dimensionless numbers, in this case just one, mu tilde, and characterize them with respect to epsilon. Go. Factorize the governing equation with respect to epsilon in this sense. So make explicit the dependence on epsilon of the different dimensionless numbers that we have introduced, and understand what are the terms of order 1, of order epsilon, of order epsilon square, of order 1 by epsilon, and so on, in the list, in the governing equation. So our governing equation now, in the end, reads like that. In the end, reads like that. Mu epsilon square Laplacian of v minus gradient of p equals 0, where I eliminated now all the tildes, because I should stay in the domain where everything is with a tilde. The Laplacian is dimensionless, the p is dimensionless, the gradient is dimensionless, the p is dimensionless. Okay, we agree that everything is dimensionless. I eliminate the tildes. Okay, but this is a dimensionless form. Okay, so you see that you have this term which is of epsilon square, and this is of order 1. So, which means this item 2. And now you come back to this hypothesis. So to the hypothesis of considering phi as a function of x and y periodic with respect to y, and you add an additional statement. So you consider what is called an asymptotic development of your unknown field. So what we are saying here is that our field phi epsilon of x, that we will apply to v and p in our case, is constructed, which is a function of x and y. So the intermediate step here is that this is phi of x and y, phi hat of x and y. This we expand in terms of asymptotic development, in the sense that we expand the function phi as a sequence of terms of different order with respect to our small parameter epsilon. So we have a zeroth order term in epsilon, plus epsilon a first order term, plus epsilon square a second order term, and so on. Okay? So we are not just introducing this form of the solution, but we are considering what is called an asymptotic expansion of it. So the main point is that we assume that the solution will be expanded in that way. Okay? So phi naught of x and y plus epsilon phi1 of x and y, and so on. Okay. So now the idea is that you have the your governing equation. You have your asymptotic expansion for your unknown. You have also the way to calculate gradients, taking into account the fact that every field will be considered as a function of x and y. And so now you put everything together, and you state the equation now in terms of no more in terms of v and p, but in terms of v0, v1, v2, and all the terms that you want to consider, p0, p1, p2, and all the terms you want to introduce. Okay. So this is the point, and clearly, when you do this job, what are you going to obtain? You are going to obtain terms of different order with respect to epsilon. So this is the job that we have to do. So when you put everything together, as there is epsilon here, but there will be some epsilon, and 1 by epsilon coming from the Laplacian of v, 0 plus epsilon v1, and so on. So there will be a combination of epsilon coefficients due to the form of the governing equation in terms as a function of epsilon, to the asymptotic expansion, and to the form of the gradient of every field split in this way. So according to this, let's say, multi-effect that we can have, the final result will be a set of governing equation parameterized by epsilon. So we will get epsilon to the power k, which multiplies a differential operator. Epsilon to the power k minus 1, another differential operator, and so on. So in the end, the only way to solve this problem will be to put to 0 the different terms of multiply the different terms multiplying the different power of epsilon. And so we will get what is called a cascade, a sequence of differential problems. So this we are going to see directly in this case in such a way that you can understand what we are speaking, what I'm speaking about. So let's let's go to our Stokes problem. Now, so as I was telling you, this is the original problem, okay, but already rewritten considering the dimensionless form, where we assumed this hypothesis on the dimensionless viscosity. So this is epsilon m, epsilon square m, v epsilon, just to stress that we are at this level for the moment. Okay. This is the divergence of V, and this is the boundary condition. Okay. So what we have to do now is to replace term by term the different. So let's try to do this calculation by hands. It's such a way that you understand what is written there. So, if we consider the this definition of the gradient, obviously we have to apply this definition of the gradient to the asymptotic expansion. So the gradient of phi epsilon will be what? If phi epsilon is this expansion, will be the gradient x of phi naught plus 1 by epsilon, the gradient y of phi naught. Okay, plus epsilon, now the same for phi 1. So the epsilon, the gradient x of phi 1 plus 1 by epsilon, the gradient y of phi 1 plus epsilon square, the gradient x of phi 2 plus 1 by epsilon, the gradient y of phi 2, and so on. Okay, so you see what is going on, because you have now terms of order 1 by epsilon, which is the largest one. No? We are considering epsilon tending to 0, so 1 by epsilon is for sure the largest one. It's larger than 1, is larger than epsilon square, and so on. So this is the largest term. Then you see that you have terms of order 1, so epsilon to the power 0, are this, but not only this. There is also that term, because that term is 1 by epsilon gradient y of phi 1, but it is multiplied by epsilon. So these two are of order 1, epsilon to the power 0. Then there are terms of order epsilon. Terms of order epsilon are this one, but not just this one. There is also that one, because it is 1 by epsilon times epsilon squared. And so on. If we are going further, obviously the structure remains the same. So you see that the gradient phi can be written as 1 by epsilon, the gradient y of phi naught, the red box, and then this, which is an iterative formulation, saying epsilon to the k minus 1 this is y-i-k k, sorry. So k running from 1 to n, epsilon k minus 1 of this, no? So for instance, for k equal to 1, we get k minus 1, so epsilon to the power 0, so 1. and then gradient x of phi naught plus gradient y of phi 1, which is exactly the summation of these two blue terms. And then for k equal 2, you have epsilon 2 minus 1, so 1 times gradient x of phi 1 plus gradient y of phi 2, which is exactly what is written here, and so on. So this is just, this is not required because everything is inside this. No, okay, because no, it's fine because in principle you can go further. I mean, this is just a finite summation, but in fact here we don't investigate we don't ask ourselves the question if this finite sum converges to a series or not. So it's purely asymptotic. What is called an asymptotic expansion is a formal expansion. We are not investigating convergence. Okay, so this is the gradient. Okay, gradient of phi epsilon. So this way of writing things should be applied to velocity and to pressure. But for velocity, we have Laplacian, in fact. Okay, Laplacian is divergence of the gradient. No? So in fact, we have to combine the derivatives. So it's a nested story. No? So the Laplacian of phi epsilon is what? Is the divergence of the gradient of phi epsilon. But so the gradient of phi epsilon, we have to use this expansion. For the divergence, we have the divergence is like a gradient. No? So we have to use also the decomposition of the divergence into divergence x plus 1 by epsilon divergence y. The divergence is just the trace of the gradient. So this means that what we are going to have is this, is divergence x of this expansion of gradient of phi epsilon plus 1 by epsilon divergence y of gradient of phi epsilon. Huh? Because of the same argument here. And so now we have to apply this divergence x and this divergence y at this whole sequence of terms. Huh? So, what do you have? What do we have? Divergence x of that is what? Is divergence x of gradient x of phi naught. So, term by term, nothing special. Plus divergence x 1 by epsilon gradient y of phi naught plus epsilon divergence x of gradient x of phi 1 plus 1 by epsilon divergence x gradient y of phi 1. I stop here, I don't put the phi 2, otherwise it's boring. But we can put, because it's better to have a complete look. Let's put plus epsilon square divergence x of gradient x phi 2 plus 1 by epsilon divergence x of gradient y phi 2. Okay? And so this is just the divergence x. Now 1 by epsilon divergence y. So plus 1 by epsilon divergence y of gradient x phi naught plus divergence y of see, I missed something. actually, no, it's fine. So divergence y, so 1 by epsilon, divergence y of gradient x plus, what was the 1 by epsilon? Plus, so the 1 by epsilon, which becomes a 1 by epsilon square, 1 by epsilon square divergence y of gradient y of phi naught, because you have the two 1 by epsilon, the one coming from the divergence y and the other one coming from here. So I'm just applying now before I apply divergence x to this, and now I'm applying 1 by epsilon divergence y to the same. So 1 by epsilon divergence y of gradient x phi naught plus 1 by epsilon square divergence y gradient y of phi naught plus so I have 1 by epsilon times epsilon divergence y of this. So divergence, divergence y of this. So divergence y of gradient x phi 1 plus 1 by epsilon gradient y phi 1 plus 1 by epsilon square divergence y of gradient x phi 2 plus 1 by epsilon divergence y gradient y phi 2. Okay, and so on. So this horrible stuff is constituted by what? So we have, first of all, highest order term is this 1 by epsilon square divergence y gradient y phi naught. It's 1 by epsilon square. Laplacian, which is this. Laplacian y by d y gradient y. Okay, then terms of order 1 by epsilon. What are the terms of order 1 by epsilon? This one, 1 by epsilon dx gradient y, then what is it? This one. Then this one. I'm sorry, here I missed the divergence. There was a divergence. I was applying divergence y. So this one, because here you have epsilon and 1 by epsilon, which simplifies. So this is over the 1 by epsilon. And then that's it. Okay, then probably there will be other terms, but not in the development that I'm considering. Let me see if I missed something. Probably there should no.
The last.
There is another one. No, I don't think so. I mean, there could be divergence.
One over epsilon times epsilon squared can simplify.
No, I think it's over. Yeah, I think it's over. Because that one. Anyway, so, then terms of order So this we put terms of order 1 by epsilon squared, terms of order 1 by epsilon, now terms of order epsilon to the power 0, huh? Minus 2, minus 1, 0, so epsilon to the power 0 is 1, so this, then that, because there is epsilon 1 by epsilon, this one, and that one. Okay. Few minutes, yes. And so here we are with the term of epsilon to the power 0, and then other terms, so epsilon to the power 1. So epsilon to the power 1 is this, epsilon, then this, epsilon square 1 by epsilon, this, and obviously if we were going further, other terms. And then there is a term of order epsilon square, which is this one. So in the end, you can, so you see that the blue one we put, okay. The green one are this. We have identified, no? Divergence, so we have divergence y of gradient x of phi naught. Divergence. This. Ah, no, sorry, this was the blue. Sorry, this was the red. I mixed the color. This was the red. Sorry. This was the red, no? So it was divergence order 1 by epsilon. So divergence x of gradient y of phi naught. This one. This means divergence. Divergence x gradient y of phi naught. Divergence y gradient x of phi naught, divergence x gradient y of phi naught, and the Laplacian y of phi 1, divergence y gradient y of phi 1. So this is fine. Then the green ones, when no, sorry, the green one, the blue, the green ones, sorry, the green ones, which are the Laplacian x of phi naught. So here for k equal to 2, with k here starts from 2, so we have epsilon to the power 0, so 1. So Laplacian of phi naught, which is the first green term there. Then divergence y gradient x of phi 1, divergence y gradient x of phi 1, divergence x gradient y of phi 1, this one, and finally Laplacian y of phi 2, which is this. And then all the other terms, if you go further with the expansion, take the same form as this last. Okay, so now we have these expressions for the gradient and the Laplacian, and so we have to apply this, we will do next time. We have to apply this expansion to our problem, because we have the Laplacian of V and the gradient of P. Okay, so we have to exploit these identities over there, keeping into account the fact that the coefficient of the Laplacian is of order epsilon square. So you can observe since starting from this calculation, sorry, you can notice that you will have in this equation different terms of different order. So we can collect in the end the equation at order 1 by epsilon, at order epsilon to the power 0, epsilon to the power 1, and so on. And all these problems will be independent because they are at different scales, and so they should be solved as a cascade of problems. So we have to identify all these problems and find a way to solve them. Okay? As you will see in the end, stopping at the first order, we will come back to the same problem as the one that we were solving before, but now defined just at the level of the unit cell. Okay, so think of that. We will, in any case, we will meet tomorrow. So we will go further in this deduction. Okay.